Hey guys, I hope you're doing well. So in this video, I'm going to tackle Lab 9 and kind of what we're going to do in it. So Lab 9 here is all about the beginning parts of Chapter 16. So, excuse me. Um, so what we're going to do is we're going to tackle vector fields. We're going to understand how to compute line integrals in a scalar form and in vector form over a vector field. So this first part, let me kind of show you the lab and let's go through that. Kind of at least what we're expecting here. Um, if you do need any extra help on this, I do have some other videos on 16.1 to 16.3 up on YouTube, so feel free to check those out to kind of help you go through these. I apparently have a great cough right now. This is great. Thanks. So in Lab 9 here, the first part of this is all about vector fields. So being able to plot them. We have this plot called a vector plot, which is nice. So if I have a vector field, let's say x minus y comma x, something like that, we can define a vector function as such, right? I have a vector function here. It has two inputs, x and y, making sure we have the underscores. And we use the curly braces when we denote a vector. And this can be a really common occurrence when we go forward here. So making sure we denote them as that. And so we can use vectors as a vector plot here. X here will just tell me kind of the domain it makes. And then vector plot kind of makes a nice vector field. I'll kind of show you what that looks like, just to kind of show that. So if I just plug this in here, in this case, let me share that. So if I kind of use this here, there's a vector plot. You should get something that looks like this. Now, this is kind of a cool field here. And kind of, I want to show you what everything denotes here. Now, this plot might look different depending on your Mathematica. It's a really important thing to remember. So this arrow is the vector that the direction it's pointing in. As well, we also have that this color scaling. If you see that over here, there's a little bit of blue. Over here, there's a little bit of like yellow. In that case, what Mathematica is doing in their newest update, if you've updated to 12, what it will do is the color scale here, this heat map, will tell you the magnitude of the vector here. So over here in these yellow parts, it's a very high magnitude. Over here in the blue parts, it's very low magnitude. In your one, possibly, if you are in Mathematica 11, you will also get you'll have actually the size of the vector will correspond to the magnitude. So it really just depends. Now there's also this other function called stream plot. And what we can do for this is, what a stream plot is, it actually will let you plot the stream, basically the streamlines here. And what exactly is a streamline? Well, a streamline is actually these lines that follow. Kind of imagine if I placed an object in this vector field. I placed an object in this vector field, kind of just let it go. Kind of just letting it follow the vector field. Where would it go? So what stream plot allows you to do is it lets you plot 10 or so stream points, and it lets you kind of just follow through the vector field here, which is kind of cool. And it allows you to visualize what would happen if I placed a point somewhere. You can even be more specific and place it in a specific part if you wanted to with this stream points command. But this is kind of what we should kind of look at. So if I started here, for instance, the vector field kind of goes in this direction and kind of follows that trajectory, kind of goes in a spiral, as it kind of expects here. And so we're going to explore that going forward here. Kind of looking more at what that is. Exercise 1 and 2 is basically, can you just plot it? There's also the plot, vector plot 3D, if I want to do three-dimensional plots. Same exact thing. It kind of looks a little bit weirder. It's kind of cool. So make sure you're on the cube, -4 to 4, in this problem at least. So the next part is all about line integrals of scalar functions. So we do have this representation. So as a reminder, what FDS actually represents, it is going to represent the area of the curtain that is formed over the curve C. So every single point on my curve C here, I'm going to have a point of the function value at that point. It's going to be kind of this sheet. We're going to hopefully visualize that. We can compute this integral by switching it to a time domain. So going from parameterization from arc length to time. And the way to do that is we can define this function vector r of t, which is going to be the curve parameterization, and we plug in all the representations where x or y. If I have x of t, I plug it in for x. If I have y of t, I plug it in for wherever I say y. And then I multiply it by the magnitude of the derivative, kind of the velocity vector, the magnitude of the basically the speed. Kind of I need to shift that over using the fundamental theorem of calculus. So this is the exact steps you always need to take to solve these. The first thing is parameterizing the curve. You need to parameterize the curve, create an x of t and a y of t. That's something we've done in the past, like line segments, right? Knowing how to do that formula, right? How to do a circle, that stuff. Then we compute the magnitude of this, and then we substitute in x and y. We substitute those in for f, and then we compute the above integral. So as an example, we kind of go through an example here, so please read this through. But what's nice here is if I have this right half of a circle, x squared plus y squared equals 4, and I want to solve this integral here, we parameterize the curve, so I can always parameterize the circle as cosine and sine, but I'm on a radius 4, a radius 2, so I need to put a 2 in front of here. Since I'm on the right half of the circle, I'm only on this part over here, so I'm going to be between negative 2, pi over 2 and pi over 2. We then calculate our prime of t. The magnitude will just come out to be 2 here, which is nice. And then what we do is we plug in x of t wherever I see x, and I plug in y of t wherever I see y. And that's kind of this part here. And so we can substitute it, and we can get this integration. And we can do this integral, making sure we multiply by 2. Mathematica, we can do this all in a snap, which is really cool. So how do we do it? We define our function. We define our function here. We then define x of t and y of t from our parameterization domain. We then calculate our norm. So we calculate this vector. So to do that, I would suggest using the norm f function here, which then corresponds to the square root of x prime of t squared and y prime of t squared. You can use this exact code almost just to change the x of t and y of t and f. And then lastly, we integrate f at x of t and y of t. This is actually really cool. So I'm able to plug in my x of t and say, okay, I want to evaluate f at x of t and y at y of t. That's kind of nice. And so what's cool is we're going to be able to visualize what this actually is. As a reminder, the interpretation here is the net area of the fence or curtain that is whose base is c and whose height is f of xy. And it's actually represented something like this. Which is kind of cool. It's the area of that. And it actually, we're able to use this using the list point plot 3D command. Okay, so go ahead and then this next part here, exercise 3, will take you through this whole entire thing. Making sure that you keep everything consistent with your function here. We're going to parameterize the curve in 2 different ways. We're going to do 2 different curves. So make sure you do that. Define them as x1 and y1 and x2 and y2. And then we have this code here that you'll be able to visualize it. Making sure here, we need to parameterize, you need to make sure you find your domain for t here and comment that. Because what you're gonna need to do is, if you're plot 1 and plot 2, you should change the things that say change. Please do, when you do that. And make sure you change your time domain. So for instance, if you're a line segment, it should be 0 to 1. Or if you're, in this case, it would be, negative pi over 2 to pi over 2. Something like that. In these, for parts D and E here, this function is going to be really tough to integrate, so definitely try to use n integrate rather than integrate. So the same exact things as integrate, but switch it to n integrate there. And also, based on your plots, see which one should be larger. Make sure of that. So lastly, this last couple parts here are all about line integrals of vector fields. So we have a vector field f, as we've had in the past, and I want to find f dot dr, which represents the amount of work it takes to move an object along a curve c in the vector field f. You can kind of imagine the vector field being, in some way, just a wind tunnel, or kind of a wind, or even a water, kind of a flow. It can be written as pdx plus qdy as well. And what's nice here is, again, if I want to evaluate this, I kind of use the same process again. It's a very similar process. I parameterize my curve C. I then find r prime of t in this case, because it's going to be a vector dotted with a vector. So I need to actually take a dot product rather than the magnitude. So be aware of that. I then evaluate x of t and y of t in for my vector field f, take the dot product, and then go from A to B. So make sure you read all of this. It's really important that you read through this whole thing. I'm kind of skipping a little bit more here. But this exercise here will let you visualize kind of what we should be expecting. Should I be expecting a positive amount of work, a negative amount of work, or zero, or something like that? Because if we're a positive amount of work, I should be going with the vector field. Negative, I'm going against. So again, here we kind of bring you through this problem, exercise 4, kind of go through the exact steps that you need to do. And this is actually kind of interesting. So R of t here, you should be defining this something as, you know, I did not mean to put up a poll. So what I mean by R of t here, if you're thinking like R of t is equal to, you know, t times t squared or something like this, right? That's what I mean. Like instead of saying x of t is equal to t and y of t is equal to t like we did up there, you can actually define, you know, in this way too. So we want you to use this full R of t here to find this vector. As we've done in like the past couple labs, maybe in like labs 3 or 4, even around that area. That's kind of what I want to do. So again, we're going to be able to visualize this. So please just copy and paste this in there. I hope this is helpful too. Make sure you change where it says change, because you should be, you know, making your parameter domain. And we're going to be superimposing here the vector field and the curve on top of each other. So you'll be able to actually see should the vector field, should this integral be negative, positive, or zero, or something like that. And what's lastly here, especially in this part, we need to replace f of xy with f of x of t and y of t. And what we can do is we can use this double at symbol, which tells Mathematica, okay, I want you to compute f at r of t. R of t is 2 components, right? R of t is 2 components. I want the first component to be for x and the second component to be for y. It's really nice. And in this nice formula, right? We need to use the dot product here because it is a dot product, right? Because we have a vector dotted with another vector. I need a scalar out of it and to integrate it. And then we want you to interpret your results here. And lastly, here we're going to talk about conservative vector fields and potential functions, right? This last little part. So in order to create, if I have a function f, we usually call this a potential function. Take the gradient of it. This gives me a vector field, right? The gradient of it. And f is a conservative vector field if this occurs. And what we can do is I can define f in 2 ways. If it's a 2-dimensional or 3-dimensional function, I can use this as the grad command. Now note here, pretty important to note that I do want to not have the colon in front. If you have the colon in front, it actually will suppress the output, and that'll be bad because then Mathematica will do some bad things. So make sure you do this without the colon. It's an important thing. And yeah, we can plot the gradient field too. And to make sure we know what the fundamental theorem of calculus is, this is kind of the fundamental theorem of line integrals, it's a really important thing to remember that if I have a conservative vector field, my integral from the past that I just had is path independent. So all I have to calculate is what happens at the end and what happens at the beginning here. So I give you, in this one, we give you the potential function, and we kind of have to show you in 2 ways how to go about it. My body just loves this. This is great. So we want you to use 2 ways, right? Evaluate it using the regular definition that we did in the past, that we just did in the last problem, or use the fundamental theorem of line integrals, right? To evaluate this function at the end point, subtract it from the starting point. That's kind of the goal. And lastly here, this last couple problems is to show you how to show that a vector field is conservative. The way you show this, as a reminder, is we assume that this is basically, if this is conservative, right, this is a fx and this is fy. So if I take the mixed partial derivative, fxy equals fyx by Claro's theorem, they have to be the same. So that's why we have to check that. So if I take this derivative with respect to y, I take this derivative with respect to x, these would have to be the same. So we know if they're not the same, then f is not conservative. And we can use this nice little handy code where this 1 tells Mathematica to take the function, the first component of f, and this 2 tells it to take the second component. So we subtract them. If it's 0, that means they're the same, right? If it's not, then that happens. So exercise 6 here, we want you to show this vector field is conservative, and then we want you to find the potential function. So we have to integrate this back up, right? Make sure we know the process, right? We integrate with respect to x, integrate with respect to y on both of them, and then kind of match them up if necessary. And then use this potential function to compute this pretty nasty integral. It's very tough for Mathematica to do just in general. And then lastly, exercise 7, just comment on what we know about conservative vector fields. Yeah, so I think that's basically it for me. I will end it there, but if you have any other questions, let me know, and I'll be around. So I hope you're doing well, and I'll talk to you soon.